In Module 4, we want to introduce and expand upon the concept of chemical equilibrium. Many reactions do not result in complete conversion of reactants to products, but rather they reach a state of what is called dynamic equilibrium. Let's consider the simple conversion of dinitrogen tetroxide, N2O4, to two molecules of nitrogen dioxide, NO2. The balanced equation for this reaction can be written here, and you'll notice that as before, I wrote the rate constant for this reaction over the arrow, but in this case, I've labeled the rate constant Kf, meaning it's the rate constant for the forward reaction. We always consider the forward reaction as going from left to right. Now, the forward reaction is actually known to be a one-step elementary reaction, and so the rate expression can be written as rate of the forward reaction equals the rate constant times the N2O4 concentration to the first power, because the coefficient in front of N2O4 is 1. Now remember from a previous chapter or module that we can only write a rate expression directly if we know that this is a one-step reaction, and here we do. So we have the rate expression for the forward reaction going from left to right. Now as the forward reaction proceeds, there's a buildup of NO2 in the reaction vessel, and this increases the probability of two NO2 molecules colliding to reform N2O4. This would be the reverse reaction of the one above, going from right to left. So we're going to reverse the arrow, and we're going to say that the rate constant for this reverse reaction is K sub R, R meaning reverse, right to left. Now the reverse reaction is also a one-step elementary reaction, and so the rate expression for this reverse reaction can be written as the rate of the reverse reaction equals the rate constant times the square of the NO2 concentration. Now eventually, the rate of the reverse reaction is going to be equal to the rate of the forward reaction, and what that would mean is that the expression Kf times N2O4 to the first power, which remember is the rate of the forward reaction, left to right, is going to equal the rate of the reverse reaction. And we said the expression for that is Kr times NO2 squared. That would be the rate of the reaction going from right to left. Now, when these two rates are equal, the rate of the forward reaction and the rate of the reverse reaction, we say that the reaction has reached equilibrium. Now we can graph the forward and reverse reaction rates starting from time equals 0 and proceeding until the rates become equal. In other words, until equilibrium is reached. So what we have here is a graph of rate on the y-axis and time on the x-axis. And we've labeled this blue line here the rate of the forward reaction, which we said on the previous slide equals Kf times N2O4 to the first concentration, first power. And the rate of the reverse reaction is labeled in orange, and we said that was equal to Kr times NO2 concentration squared. And you'll notice that the forward reaction rate decreases with time, and the reverse reaction rate starts at 0 but increases with time. That's consistent with what we said on the previous slide. At first, the only reaction is from left to right, the forward reaction, and the reverse reaction is not occurring. But as time proceeds, the forward reaction starts to slow down, the reverse reaction starts to speed up, and eventually at a certain time, the two rates become equal. So in this region, after we've crossed this time threshold marked by this dashed line, the rate of the forward reaction equals the rate of the reverse reaction, and we say equilibrium's been reached. Now you want to note here that at this point the reaction has reached a state of dynamic equilibrium. Dynamic means moving. The forward reaction is still occurring, but at the same rate as a reverse reaction. Now, to our eyes in the lab, the reaction appears to have stopped. However, it has not actually stopped. It has reached a state of dynamic equilibrium where the measured concentrations of reactant and product are no longer changing. So it appears to us that the reaction has stopped because the concentrations of N2O4 and NO2 don't seem to be changing, but that's because they're in dynamic equilibrium. The rate of the forward reaction equals the rate of the reverse, and we say that the reactant and product concentrations have reached their equilibrium values. From the previous slide, we said that at equilibrium, the rate of the forward reaction, Kf times N2O4 to the first power, equals the rate of the reverse reaction, Kr times NO2 to the second power. We can rearrange this equation by simply taking N2O4 concentration and bringing it under the other side of the equation. In other words, I'm going to divide both sides by N2O4 bracket, and then we'll divide both sides by Kr, effectively bringing Kr underneath Kf. And so if we do that, we'd have N2O squared concentration divided by N2O4 concentration equals the forward rate constant divided by the reverse rate constant. Since these are both constants, then the entire expression here is a constant, which we'll call capital K. And this will be called the equilibrium constant for this reaction. Now the equilibrium constant K, capital K, for any reaction really is a constant at a particular temperature. Now it makes sense that K would change if the temperature changes, since both rate constants forward and reverse are temperature dependent, and they're most likely temperature dependent in a different way, so that the equilibrium constant K would change if you change the temperature. So keep in mind when we talk about equilibrium constants, they're constant as long as the temperature doesn't change. Now in this course we will put much more emphasis on how the equilibrium constant K is derived from a ratio of concentrations. You see here's a ratio of concentrations being equal to the equilibrium constant, rather than a ratio of forward and reverse rate constants. So we're going to express equilibrium constants capital K as a ratio of concentrations. So for example, for our equilibrium that we've been dealing with here, the equilibrium constant is equal to the square of the NO2 concentration divided by first power of the N2O4 concentration. And we've replaced our forward and reverse arrows with forward and reverse half arrows. This is considered to be an equilibrium sign here, and so we use half arrows often. Sometimes, depending on the word processor, we have to use two full arrows going in either direction, or a double arrow. But you'll see this equilibrium sign most often when an equilibrium exists. Now you notice I added a subscript C to the equilibrium constant here, and we're doing that just to clarify the fact that the equilibrium constant is expressed as a ratio of concentrations, the C coming from concentrations, in units of molarity. Now an expression in terms of molar concentrations for the equilibrium constant K for any reaction in general can be derived as follows. Suppose we have a generic equilibrium. We'd say that the equilibrium constant Kc for this equilibrium is the concentrations of the products, the molar concentrations of the products, each raised to the power of their coefficients in the balanced equation, divided by the product of the concentrations of the reactants, each reactant raised to the power of its coefficient in the balanced equation. Now this relationship here is often referred to as the law of mass action. Kc, of course, is the equilibrium constant, and the ratio of the concentrations, all raised to the appropriate powers, is typically called the equilibrium constant expression. And I will use these two terms going forward. So when I say equilibrium constant, I mean the numerical value of the equilibrium constant. The equilibrium constant expression will be the ratio of concentrations written in the appropriate way. Let's look at a different reaction for a second here. This is a reaction that comes to equilibrium, nitrogen and 3 hydrogen molecules in equilibrium with 2 molecules of ammonia. If I asked you to write the equilibrium constant expression for this reaction, you'd say, okay, products go on top, concentration of products, there's only one product, it's raised to the power of its coefficient, divided by, there's more than one reactant, so we're going to multiply the concentrations of the reactants by each other, each reactant concentration raised to the power of its coefficient, a 1 for the nitrogen, a 3 for the hydrogen, and we'd say the Kc for this reaction is this equilibrium constant expression. We can also deal, of course, with reactions in aqueous solution. And so for this equilibrium, the equilibrium constant Kc would be the product of the concentrations of the products, each raised to the power of the coefficient in the balanced equation, divided by the concentration of the reactant. Interestingly, a reaction can approach equilibrium from either the reactant or product side. Now, I just threw a lot of information on the slide, but we're going to once again look at our example, our first example reaction of N2O4 in equilibrium with 2 molecules of NO2. And of course, the way we've written this, we consider N2O4 to be our reactant because it's on the left side, and NO2 to be our product because it's on the right side. Now this table, which comes from the Brown General Chemistry book, has data for this reaction, and instead of looking at the table right away, you'll see 4 experiments are done. We're going to pick out 2 experiments from this table and talk about them. And interestingly, I'm going to look at experiment 4 first. And the reason I'm doing that is because experiment 4 starts out initially as one would expect. In other words, I've built a little mini table here, and initially, before any reaction occurs, there's 0.02 molar N2O4 and no NO2. And in the table from the textbook, you can see it's the initial concentration of N2O4 in experiment 4 is 0.0200, and the initial concentration of NO2 is 0. And then I extracted some more data from the table and said, when the reaction reaches equilibrium, it's found that there's 0.00452 molar N2O4. You can see it in the table here, and I've put it in my little mini table. And there's 0.0310 molar NO2. So the concentration of N2O4 has dropped, which makes sense. Some of it reacted, and you form from some NO2. They are now at dynamic equilibrium, meaning the rates of the forward and reverse reactions are the same, so the concentrations have stopped changing. And if we calculate the Kc value here, remember the Kc value is the ratio, the correct ratio of concentrations when the reactions reached equilibrium. So we put in the equilibrium concentrations of NO2, 0.0310, and square it because that's what the law of mass action tells us we need to do if we're writing this expression correctly. And we divide by the first power of the concentration of N2O4, 0.00452, and we get the value 0.213 for our equilibrium constant. Now remember, we've done this by starting with just reactant and no product and letting the reaction come to equilibrium. Now in experiment 1, if you look on the table, the opposite occurs. So in other words, and what I mean by the opposite is, instead of starting with reactant, this experiment actually starts with the product and no reactant, which seems somewhat counterintuitive, but remember, this equilibrium wants to reach equilibrium. And this initial start here is not at equilibrium. So the reaction will go in reverse until it reaches equilibrium and until the reverse reaction equals the forward reaction. I should say the rates of the two reactions become the same. Now when this happens in this case, the concentrations of N2O4 and NO2 at equilibrium are different than in the first experiment when we started with reactant, no product. So you'd expect the Kc value to be different. Well, it better not be because it's a constant, and it's not. If you put the values in the proper expression, we come out with the same value of the equilibrium constant within experimental error. So what we've done is we've approached equilibrium from the reactant side and from the product side, and we get the same equilibrium constant, which we should if the temperature is the same. So it's important to note that when equilibrium is approached from different sets of initial conditions, the equilibrium constant Kc is the same, even though the equilibrium concentrations themselves are different. We need to spend some time talking about some useful information about equilibrium constants and equilibrium constant expressions. This will be a rather long list that takes up most of the rest of the lecture. So let's get started. For reactions involving gases, equilibrium constant expressions can be written in terms of partial pressures of reactant and product gases rather than molar concentrations. So in other words, for our sample reaction that we've talked most about, we can write an equilibrium constant in terms of partial pressures. So you can see that instead of the molar concentration of NO2 squared on the top, we have the partial pressure of NO2 squared, and on the bottom we have the partial pressure of N2O4. Both of these pressures would be in units of atmospheres, and the equilibrium constant K, instead of having a subscript C, has a subscript P, which just means that we're expressing the equilibrium in terms of partial pressures in units of atmospheres. Now you might ask, what's the relationship between Kp and Kc? They're often not the same number. So the conversion of Kp to Kc, or from Kc to Kp, can be done using this equation here. And here, R is our gas constant, T is temperature in Kelvin, and delta N is a somewhat mysterious quantity until you try a few of these. It's not hard, but it's good to look at a couple of examples. We'll look at one here. It's the number of moles of gaseous products minus the number of moles of gaseous reactants in the balanced equation. For our sample reaction here, we said that Kc equaled 0.211 at 100 degrees C. So what would its value of Kp be? Well, Kp equals this expression here, so I'll put in 0.211 for our Kc. We'll put in 0.08206 for the gas constant. We'll put in 373.15 for the temperature. That would be 100 degrees C in terms of Kelvin. And this delta N here is 1 because delta N is the number of moles of gaseous products. Remember, products are on the right, so there's 2 moles of gaseous products minus the number of moles of gaseous reactants. There's 1. So basically, this expression here is raised to the first power, and we find out that Kp is equal to 6.46. So it's not equal to Kc, but it is the equilibrium constant expressed in terms of partial pressures. You'll notice we didn't show any units here. That was intentional. And you want to note that for reactions involving gaseous products and reactants, Kp could equal Kc, but that's only when the number of moles of gaseous products equals the number of moles of gaseous reactants. So if delta N turns out to be 0, then of course this term here to the 0 power would be 1, and Kp would turn out to be equal to Kc. But that's the only time when the two values, Kc and Kp, would be the same. Now here's some tips involving working with Kps and Kcs. First of all, delta N is determined only using the gaseous reactants and products in a reaction. In some cases, delta N could turn out to be a negative number. You just have to do the algebra. And it is possible that you could be given a Kp and asked to solve for Kc. That just involves a little different algebra than the simple algebra we showed here. Okay, let's get on to more useful information about equilibrium constants and equilibrium constant expressions. Equilibrium constant expressions, and thus equilibrium constants, are written without units. Now this may seem counterintuitive if you usually pay attention to units, but let me show you using our example reaction. If we write the Kc value, I should say write an equilibrium constant expression for this equilibrium, of course, it's here. And from experiment 1 in that table, we had 0.0172 molar squared divided by 0.00140 molar, giving us this value, and we didn't put the units of molarity in. If we included units, it would look like this. And of course, what that would mean is that you wouldn't get rid of these molar units entirely. Kc would have units of 0.211 molar. Well, despite how reasonable this looks, we will not include units in these types of calculations. And the reason for this is that very precise work with equilibrium constants and equilibrium constant expressions actually involves using units called activities rather than molarities or partial pressures. Activities have no units. Now, for our purposes, K values derived from molarities or partial pressures will be acceptable. And so to just be consistent with the most precise work involving units of activities, we will not include units in equilibrium constants or equilibrium constant expressions. That probably doesn't disappoint you. Here's even more useful information about equilibrium constants and equilibrium constant expressions. It turns out that pure solids, anything labeled with an S in an equation, or liquids, anything labeled with an L, appear in equilibrium constant expressions as simply the number 1. Heterogeneous equilibria, more than one phase present, are easily handled but can result in some seemingly strange-looking equilibrium constant expressions. This statement seemed to come out of the blue here, but if you have an equilibrium where you have more than one phase present. So let's say you have solids and then you have gases or things dissolved in water. You have things in more than one phase. We call these heterogeneous equilibria for obvious reasons. Let's just look at some examples to see how this works out. The autoionization of water is an equilibrium we'll deal with in future chapters. Water is actually capable, liquid water, of decomposing into dissolved aqueous H plus and aqueous OH minus ions. This comes to equilibrium, and we can write an equilibrium constant for it. It would be the concentration of the products multiplied by each other, coefficients are 1, divided by the concentration of liquid water. Here's where we invoke our rule 3 here. We have an L after the water. It's considered a pure liquid, so we substitute a 1 for the concentration of liquid water, which means the equilibrium constant expression just turns out to be the product of the H plus and the OH minus concentrations. How about this reaction? This is a description of the precipitation of lead 2 chloride from aqueous lead and chloride ions. Well, we can write a Kc for this. It would have lead chloride solid on the top divided by the concentration of lead 2 plus times the concentration of chloride squared. Again, since this is a solid, we just substitute a 1, which means the equilibrium constant expression turns out to look like that. Again, notice a 1 was substituted for the solid lead chloride. Now the magnitude of K gives information about whether reactants or products dominate when equilibrium is reached, or whether there's a significant quantity of both reactants and products at equilibrium. This turns out to be a handy rule or guideline, and it involves making a judgment from how large a number or small a number the equilibrium constant is. How large or small it is gives us some information about that reaction when it reaches equilibrium. If K is much, much greater than 1, meaning it's a big number, we say that's a large K, then that turns out then products must predominate at equilibrium. That is, the equilibrium lies to the right, or in other words, it favors the right side of the reaction. If K is a very small number, we say a small k, much, much less than 1, then reactants predominate at equilibrium. We'd say the equilibrium lies to the left. In other words, the reaction favors the left side or the reactant side at equilibrium. Consider the reaction carbon monoxide plus chlorine going to COCl2. This comes to equilibrium, and it has a rather large equilibrium constant at 100 degrees C, 4.56 times 10 to the 9th. That's truly much greater than 1. Let's write out the equilibrium constant expression according to the rules. It equals this number. Now, if this is true, it means that at equilibrium, the concentration of COCl2 must be very large relative to the concentration of CO and Cl2. In other words, at equilibrium, there's a huge amount of product and a very tiny amount of reactant left. That's the only way you'd get this large of an equilibrium constant. So we'd say this equilibrium is product favored. It favors the right side at equilibrium. In fact, this Kc is so large that we'd probably say this reaction essentially proceeds to completion, because this number is so large, it's telling us that the concentration of reactants at equilibrium is ridiculously small. There's hardly any left, and the concentration of product is very large. How about the autoionization of water that we talked about or presented before? Well, the Kc for this equilibrium is quite small. It's equal to 1 times 10 to the minus 14 at 25 degrees C. That truly is much less than 1, so it's a very small K. If we write out the expression for Kc, of course, for water, we have a 1, and so Kc equals H plus times OH minus. That number turns out to be 1 times 10 to the minus 14. Well, what does that tell us? It tells us that at equilibrium, extremely little water has ionized to H plus and OH minus because the product of the H plus and OH minus concentrations at equilibrium are ridiculously small. So we say the equilibrium for this reaction favors the reactant side. In other words, at equilibrium, it's still mostly just liquid water when it reaches equilibrium. In fact, this Kc is so small that we often ignore this reaction when we talk about acid-base reactions in future chapters. We say we're going to ignore the contribution of liquid water to the concentrations of H plus and OH minus since this equilibrium so strongly favors the left side. One thing you might ask here is, what about cases where K is neither huge, meaning it's way bigger than 1, or tiny, much less than 1, but somewhere in between? Well, first one has to settle on a definition of what we mean by somewhere in between. So if we define this as somewhere around K equals to 1, maybe a range of 0.1 to 10, with 1 in the middle, we would say that in these cases, there are significant quantities of both reactant and product still around when the reaction reaches equilibrium. Okay, yep, there's even more useful information about equilibrium constants and equilibrium constant expressions. If you reverse the way you write a reaction, the equilibrium constant for this new situation is the inverse, meaning what we mean here actually is the reciprocal of the original equilibrium constant. So from the previous slide, remember we said that CO and Cl2 come to equilibrium with CoCl2, and that equilibrium strongly favors the product side. We'd write the equilibrium constant expression like this, and we know it equals 4.56 times 10 to the ninth. Now, if we chose to write the reaction in reverse, meaning we chose to call the CoCl2 the reactant and CO and Cl2 the product, we can do that, but remember the new equilibrium constant will be the reciprocal of the old one, just if we follow the rules, because CO and Cl2 are now the products. They go on top. Concentration of CoCl2 goes on the bottom. If we do that, we have to also, if we take the reciprocal of this ratio, it means we need to take the reciprocal of this number. So the equilibrium constant for the reaction written this way is 2.19 times 10 to the minus 10. It's now suddenly ridiculously small. Now, this makes sense. Both the values of Kc, the large one, and Kc prime, the tiny one, gives us the same information. When equilibrium is reached, the mixture will be almost exclusively CoCl2. If we write the reaction this way, we say the equilibrium constant's huge, meaning at equilibrium it's almost all CoCl2. If we choose to write it in reverse and call CoCl2 the reactant, the reality can't change. It's mostly still CoCl2, and so it's now mostly reactant because we wrote it differently, and so the equilibrium constant is now tiny, which means yes, it stayed mostly in the form CoCl2. Another way of stating this is, look, if we initially have CO and Cl2 in a container, they have a great tendency to react and form CoCl2. If initially you put CoCl2 in a container, it has very little tendency to decompose into CO and Cl2. So the magnitude of the equilibrium constants, and of course the way we're writing the reaction, gives us a lot of information about the chemistry going on here. Yes, there's even more. Turns out if you multiply all the coefficients of a balanced equation through by a constant factor, the new equilibrium constant will be the old equilibrium constant raised to the power of that constant factor. The best way to describe this is to just show you an example. So from the current reaction we seem to be concentrating on, remember that carbon monoxide and chlorine are in equilibrium with CoCl2, although the equilibrium strongly favors the product side because the equilibrium constant is large, and we write the equilibrium constant expression as this. Now let's suppose, for whatever random reason, we wanted to multiply this balanced equation through by 3. So each of these coefficients is a 1. If we multiply through by 3, each of the coefficients will be 3. So you might ask, does this affect the equilibrium constant? Well, it doesn't really affect the chemical fact that the reaction favors the product side, but it does affect the equilibrium constant because it affects the equilibrium constant expression. So if we wrote an equilibrium constant expression for this, we have to concede the fact that there are now coefficients of 3, and so we'd have to raise each of these concentrations to the third power, which means effectively we're taking our equilibrium constant number and raising it to the third power. So the Kc of the reaction written this way is actually 9.48 times 10 to the 28th. So let's look at our statement up here. If you multiply all the coefficients of a balanced equation through by a constant factor, which I did here, I multiplied it through by a constant factor of 3, the new equilibrium constant, Kc prime, will be the old equilibrium constant, Kc, raised to the power of that constant factor, 3. And that's what we did. What happens if we multiply through by a different factor? Suppose we multiply through by a factor of 1/2. Well, we follow the same guidelines. The new Kc will be equal to the old Kc up here, raised to the power of the factor we multiplied through by. In other words, raised to the 1/2 power. We're effectively taking the square root of this K value, and we'd get a value of 6.75 times 10 to the 4th. Now, despite appearances, this seemingly uninteresting piece of information about equilibrium constants will come in very, very handy later. One more thing. If you add 2 or more balanced equations together, which we've done in the past, to get an overall net reaction, the value of K for this overall net reaction is not the sum of the equilibrium constant values, it's the product of the equilibrium constant values of the individual reactions used in the summation. So here's an example. Let's suppose you have these two equilibria, and they're gases, and this time we have values of Kp for these. So the Kp for the first equilibrium is 28.09. Didn't write the equilibrium constant expression, just gave you the number. So it slightly favors NO2-NO-Br2 formation. And the equilibrium constant for the second equation here is quite small. Now let's suppose for some random reason I asked you to add these two equations together and come up with a net overall reaction. So we could do that, and you'll notice that there's something in common on both sides of the equilibrium signs. The two NO molecules cancel out on either side. Nothing else cancels. So if we add up everything on the left of the equilibrium sign and everything on the right, we'd end up with what we would call the net overall reaction. And then you ask, well, what would the equilibrium constant be for this? Well, as I said above, it's not the sum of the equilibrium constants, it's the product. So we'd say the Kp for this net reaction is equal to the product of these two Kp values, which in this case would be 1.34 times 10 to the minus 29. Now finally, let's try an example that incorporates many of the previous pieces of useful information about equilibrium constants and equilibrium constant expressions. Our job here is to calculate the value of Kc for the following reaction that comes to equilibrium, and we'll do that by using some given information. And the given information is that the equilibrium constant Kc for this equilibrium here is 4.5 times 10 to the minus 4, and the equilibrium constant for this equilibrium here is 1.1 times 10 to the minus 9. Again, our job is to come up with the Kc value for this reaction here, which we'd call our target reaction. So our job here is to somehow manipulate these given reactions so that when they're added together, they give us the target reaction. And then we'll know how to deal with these Kc values. So the first thing I'm going to do is I'm going to multiply equilibrium 1 through by a factor of 2. So I multiply this equilibrium right here by a factor of 2. So instead of 1, 1, 1, we'll have coefficients of 2, 2, and 2, which means by one of our previous rules that the Kc for this new equilibrium here is equal to the old Kc raised to the second power. We're going to square it. Now you might ask, why did you multiply through by 2? The reason is because you'll notice in our target reaction that HNO2 is on the left, so I wasn't interested in reversing this equilibrium. But there's a 2 in our target reaction, so I'm going to multiply through by 2, so I end up with 2 HNO2 on the left of the equilibrium sign. You also notice that there's a 2 NO2 minus in the target reaction, and that gives us, by multiplying through by 2, we get our 2 NO2 minuses on the right of the equilibrium sign. Now I'm going to simply reverse equilibrium 2. So I'm going to take this equilibrium and write it in reverse. So now we have 2H plus SO3 2 minus on the left in equilibrium with H2SO3. If I do that, following the previous rules, that means I have to take the reciprocal of this Kc and put it here. That would be the Kc value for the reaction written in reverse here. Now, believe it or not, we're ready to add these two reactions together. Again, before we go on, you'd ask, why did I reverse equilibrium 2? Well, because equilibrium 2 had H2SO3 on the left of the equilibrium sign, and I want it on the right in the target reaction, and it had SO3 2 minus on the left in our target, and it's on the right in this reaction. That's why I reverse this. We're ready to add these up because when we do that, the hydrogen ions cancel out between the two reactions. And if we just add up what's left on the left of the equilibrium sign And on the right of the equilibrium sign, you see we get our target reaction. Now we're ready to get the Kc value for our target reaction by just taking the product of these two Kc values. So K overall, meaning the overall net reaction here, or of our target reaction, is the Kc value for this reaction, which was 4.5 times 10 to the minus 4 squared, times the Kc value for this reaction, which was a reciprocal of 1.1 times 10 to the minus 9, and I get an overall K of 1.8 times 10 squared, which means this reaction, this equilibrium, favors the product side, but not overwhelmingly so.